So I've got an assembly. There's a distributed load on it. I've got a rod kind of holding it up. I've got some pins holding everything in place. So I know that the yield stress and tension of that rod is 36 ksi, and the shear on the pins is 18 ksi. So what I'm trying to find here is the factor of safety on all of these things. So the first thing I need to do is kind of figure out what's going on at those pins, okay, which will in turn give me what's going on with those rods. So I'm going to start with the free body diagram, right? I've got AX, I've got AY, I've got B right there, and I'm going to redraw that distributed load as 4 feet times 500 pounds per feet, like so. So that would be 2,000 pounds acting right at the center. Okay, so from that, now I'm going to go ahead and find AX, AY, and B. Okay. So if I put my Y there, things got a little screwed up on that. Apologize. Okay, so if I sum the forces in the X direction, I get AX minus 3/5 B. This is a 3, 4, 5 triangle. If you're not clear, be 4, 3, 5. So it's, oh no, other way around. 3, 4, 5. So it is 3/5 B. Excuse me. Same thing in the Y direction. Very similar equation. Just have a 2,000 on there, which is going to be AY plus 4/5 B minus 2,000 equals 0. I'm going to go ahead and sum the moments about A. And I'll get, on this one, I'll have a negative 2 feet times 2,000 plus 3 feet times 4/5 B equals 0. So from all this, I can find that B equals 1667. I find AX equals 1,000. And I find AY equals 667. Okay? So now I've got all of those reactions. So let's start by figuring out what's going on with the tension, right? So again, sigma is going to equal that force B, right? Because that's the force going through that rod divided by the area, which is going to be pi over 4 d squared. Okay? So from that, I can find that B is 16, oops, one too many sixes. Divided by pi over 4 times the diameter of that rod, which is 0.4 inches squared. So this is all pounds and inches. What I get is 13.3 KSI on this guy. So my factor of safety when it comes to this then becomes that 36, which is the allowable stress, divided by what my actual stress is, which means 2.71, right? So basically it's the allowable stress is 2.71 higher than the actual stress being there. So that's how we do factor of safety, is just the ratio of the allowable over the actual. Okay, so we're going and we're finding all of the actuals, and we're going to then divide the allowable by those. Okay, so now let's go ahead and do the shear stress on B, right? Well, that's going to be the shear stress, right? So now this is pin B, right? Which is, it has a diameter of 0.3, right? So that's going to be that shear force, now this is a double lap joint again, right? You've got that fork there. So like half of B is seen on either side of that pin. So you've got that double lap joint. So instead of 1677, it's going to be 1667 divided by 2, and then divided by the area of that pin, which is pi over 4 times 0.3 inches squared, right? So because of the double lap joint, I half that force going on that pin B, and from that I get a shear stress of 11.8 KSI. So the factor of safety on this one then is going to be 18 KSI divided by 11.8 KSI, and I get a factor of safety at pin B of 1.53. Okay, so again, still below the allowable. The allowable is about 1.5 more than what it is currently seeing. Okay, now at A, I've got two shear forces, right, on that pin A. The pin doesn't care what you call X and Y axis. The pin cares about the total force acting on it. Okay, so the total force acting on it is the square root of the sum of the squares. Now, again, I've got a double lap joint at A. So to deal with A, it's going to be the square root of the sum of the squares. So it's going to be 1,000 squared plus 667 squared. And then divide that by 2. And again, I'm just trying to find the total magnitude of the shear forces acting at A. I have 1,000 in the X, 667 in the Y, so the square root of the sum of the squares gives me the magnitude of that shear stress. Dividing it by 2 because I have a double lap joint. Then I take that and divide it by pi over 4 times 0.3 squared, like so. From that, I get 8.5 KSI. That gives me a factor of safety of 18 divided by 8.5, which equals 2.12. So again, find the internal forces, divide them by the area, and then to find the factor of safety, you then take the allowable stress divided by the actual stress that's being seen.